In this video, I'm going to explain molecular vibrations and show how they connect to character tables. Let's start by defining vibration. For our purposes, a vibration is the periodic oscillation of parts of a molecule where atoms move back and forth around their equilibrium positions. So how many different vibrations can a molecule actually have? A molecule with n atoms has 3 n degrees of freedom, which describes all possible types of motion. These fall into 3 categories. Translation, which is the movement through space in the x, y, and z directions. Rotation, which is the rotation about the x, y, and z axes. And vibration, which again is the oscillation of atoms within the molecule. Translation always accounts for 3 degrees of freedom, so removing those leaves 3n minus 3 degrees of freedom for rotation and vibration combined. Next, we remove the rotational degrees of freedom. Linear molecules can rotate meaningfully about only 2 axes, while non-linear molecules can rotate about 3 axes. So this gives us some key results. For linear molecules, we have 3n minus 5 vibrational degrees of freedom, and for non-linear molecules, we have 3n minus 6 vibrational degrees of freedom. Let's look at a few examples. Sodium. It's a single atom, it can translate, but it cannot rotate or vibrate. So we have 3 times 1 minus 3, which equals 0. Carbon dioxide is a linear molecule with 3 atoms. So we have 3 times 3, which is 9, minus 5 equals 4 vibrational modes. Water, or H2O, is non-linear. So we have 3 times 3 minus 6, which gives us 3 vibrational modes. And an important note is some of these vibrational modes can be degenerate, meaning they have the same energy even though the atoms move in different directions. They're basically the same vibrational mode. So now that we know how many vibrational modes to expect, we can start to visualize what these vibrations actually look like. For carbon dioxide, the molecule can vibrate in the following ways: a symmetric stretch, an asymmetric stretch, and bending in 2 perpendicular directions which are degenerate. For water, the molecule can stretch symmetrically, stretch asymmetrically, and bend in a scissoring motion. So now we know the vibrational modes these molecules can have in theory, but how do we observe these vibrations experimentally, and why are they useful? When a molecule vibrates, it can cause a change in its dipole moment. If so, it can interact with infrared light. So by shining infrared light on a molecule and measuring which frequencies are absorbed, we obtain an IR spectrum. Each molecule produces a unique IR pattern because stronger bonds and certain modes vibrate at different frequencies, and vibrations that cause larger dipoles change the absorbance intensity. In other words, vibrational modes give rise to the absorption bands we see in vibrational spectroscopy. Each mode involves specific bonds stretching or bending, and because bonds differ in strength and mass and mode, they cause different dipoles, so they appear at different frequencies. And this allows us to connect spectral peaks directly to specific bonds and molecular motions, helping us to determine molecular structure, bonding environment, and even geometry. However, not all vibrational modes are IR active. A vibrational mode is only IR active if it changes the molecular dipole moment. You can think of it like a marble shifting its color around, where the position of color changes, but the object itself doesn't necessarily become easier to deform. Some vibrations don't change the dipole moment, but instead change the polarizability, which describes how easily the electron cloud can actually be deformed or distorted. In this case, the better analogy compared to a marble is a balloon. The electron density is more spread out and becomes squishier and interacts more strongly with light, producing Raman scattering instead of IR. The symmetric stretch of carbon dioxide is a classic example. It doesn't change the dipole moment and is therefore IR inactive, but it does change the polarizability, making it Raman active. Many vibrations can be both IR and Raman active. However, for molecules with a center of symmetry, the mutual exclusion principle applies, which is vibrations that are IR active are Raman inactive and vice versa. This is why IR and Raman spectroscopy are complementary techniques to each other. So manually tracking every bond motion to find vibrational modes quickly becomes tedious and even confusing. So instead of thinking about IR spectra in terms of individual bond movements, it's more useful to think of it in terms of vibrational modes of the whole molecule. By knowing a molecule's point group and its vibrational modes, we can predict how many IR active peaks should appear in the spectrum. Symmetry tells us that modes are allowed while bond stretches and molecular environment determine the exact peak position, intensities, and width. In real systems, these peaks may shift or split slightly, but symmetry provides the essential framework for interpreting IR spectra. So from now on, we'll think of molecular vibrations in terms of symmetry using character tables, which gives us a more cleaner and more reliable approach. From earlier videos, we learnt that an irreducible representation acts like symmetry labels or codes that describe how a molecule behaves under certain symmetry operations. And character tables also tell us which vibrational modes are IR active or Raman active. The key idea is simple. If a vibrational mode transforms like X, Y, or Z, it's IR active because the vibration causes the electron density to shift back and forth along an axis, creating a changing dipole moment and respecting the symmetry of the irrip. If a vibrational mode transforms in X squared, Y squared, Z squared, or XY, it's Raman active because the vibration changes the polarizability of the molecule. In other words, the electron cloud spreads out or becomes more easily distorted as the atoms move apart in different dimensions. So instead of analyzing every vibration visually, we determine the molecule's point group, assign symmetry labels to each vibrational mode, and use the character table to immediately see whether each mode is IR or Raman active or both. Let's start with H2O as an example. Water belongs to the C2V point group and has 3 vibrational modes as seen before: a symmetric stretch, an asymmetric stretch, and a bending or scissoring mode. Using the character table, we apply each symmetry operation to the molecule and ask which bonds are unchanged. Doing this gives us the reducible representation 2, 0, 0, 2, where 2 means 2 unchanged bonds, 0 means 0 unchanged bonds. This reducible representation is simply a summary of how all the vibrational motions behave under symmetry. When we reduce it or break it apart, we find it is composed of the irreducible representations A1 and B2. This therefore tells us the symmetry of the vibrational modes. The symmetric stretch and bend remain symmetric under all operations, so they are A1, and the symmetric stretch changes under certain operations, so it's B2. Looking at the character table, both A1 and B2 transform like Cartesian coordinates or quadratic functions, which means all 3 vibrational modes of H2O are both IR and Raman active. So we expect 3 IR peaks. Now let's consider a molecule of form XY3, such as sulfur trioxide or boron trifluoride, which both belong to the D3H point group. These molecules have 3n-6 or 3 times 4 atoms minus 6, which gives us 6 vibrational modes. Now, considering how every symmetry operation affects each bond will only give us 2 of the irrips involved. So this trick only works sometimes for all the involved irrips. So the reducible representation will reduce to A1 prime, E prime, and A2 prime. A1 prime is Raman active only, E prime is both IR and Raman active and is doubly degenerate, and A2 prime is IR active only. As a result, a D3H molecule like SO3 shows 2 IR absorption bands, one from the E prime and one from the A2 double prime, even though it has 6 vibrational modes. For our final example, let's consider sulfur hexafluoride, which belongs to the highly symmetric OH point group with 7 atoms. So it has 3n-6, or 3 times 7 minus 6, which equals 15 vibrational modes. When the vibrational representation is reduced, we obtain A1G, EG, T1U, T2G, T2U, and we can compare these to the character table. It's also important to note that in this example, the molecule has a center of inversion, or a center of symmetry, so the mutual exclusion principle applies here. So for the G modes, they are all Raman active, as you can see in the character table, and the U modes are IR active. Only the T1U mode is IR active, and it's triply degenerate, meaning sulfur hexafluoride shows just one IR absorption band, despite having 15 vibrational modes. So by using symmetry and character tables, we can predict how many vibrational modes exist and which ones appear in IR or Raman spectra without needing to track every bond motion by hand. So that's about it. I'll leave some practice questions. Otherwise, feel free to leave a comment if anything needs further explanation. Otherwise, thank you for watching. Till next time.